Hello everyone, my name is Cassie Chen. Thank you for the opportunity to present my final project for CSCIE 89, Deep Learning. The title of my work is Extract Store Sentiment from News Headlines. In this project, we systematically compared the three deep learning architectures to automate the task of classifying sentiment from news headlines, a critical component for data-driven trading and market analysis. Now, let's start with why this matters. Financial markets are information-driven. News headlines, often short, punchy, and packed with meaning, can swiftly sway investor sentiment and move stock prices. Manually analyzing the sheer volume of financial news is impractical. Hence, we need automated, scalable sentiment analysis systems. This project aims to compare the effectiveness of three models for this task. LSTM, a traditional recurrent neural network as our baseline. BERT, a powerful general-purpose transformer. FIMBER, a financial domain-adapted version of BERT. We ask, what is the accuracy of each model? How much do transformers improve over LSTMs? And does domain-specific pre-training FIMBER outperform a general model BERT? The answers can guide model selection in real applications like trading algorithms and risk monitoring. The experiment was built on a public dataset from Hugging Face, Invest in Financial News Headlines. It contains 13,259 headlines, each annotated as negative, neutral, or positive. The distribution is fairly balanced, roughly 28% negative, 30% neutral, and 42% positive. These headlines are characteristically short, averaging only 12 tokens, which presented a challenge. Models must extract sentiment from very limited context. We converted sentiment labels negative, neutral, positive to numerical values 0, 1, 2, and split the data 60, 20, 20 into training, validation, and test sets, resulting in 7,955 trading samples, 2,652 validation and test samples for a robust evaluation. Here is a sample of original dataset, and the dataset is publicly accessible via the Hugging Face link shown here. We compared the three distinct architectures. LSTM, a stacked recurrent neural network with about 0.52 million parameters. It used an embedding layer, two LSTM layers, and served as our traditional benchmark. BERT-based, the standard BERT transformer with 110 million parameters, pre-trained on general English text. It represents modern context-aware language understanding. FIMBER had the same architecture as BERT-based, but was pre-trained specifically on financial corpus like earnings calls and SEC filings. This allows us to test the value of domain adaptation. The experimental process included data preparation, model configuration, model training, and performance evaluation. All experiments were conducted in a Google Colab environment using an NVIDIA A100 GPU to ensure consistent and efficient training. For the LSTM baseline, the pipeline is fairly classical for sequence modeling. First, convert text to lowercase and remove punctuation, and build a vocabulary of 5,000 words from the training set. Then convert each headline into integer indices and paddle truncate sequences to a fixed length of 20 tokens. Last, convert labels into one-hot encoded vectors. We trained the model for 20 epochs with a batch size of 128, using Adam optimizer and a learning rate of 0.001. Loss function is categorical cross entropy. Early stopping was implemented with patience equals to 5 for accuracy monitoring to prevent overfitting. The training history showed a classic pattern. Training accuracy rose quickly above 90%, but validation accuracy plateaued around 71 to 72% after just a few epochs. This indicates the model's limited ability to generalize beyond the training data, a known challenge for RNNs with relatively small datasets. For BERT and Finber, we used the Hugging Face Transformers library. The data pipeline differs in several important ways. Both models use their own built-in tokenizers, which perform word-piece segmentation. Headlines are padded or truncated to 30 tokens, which is appropriate for the short test. Labels remain as integers since PyTorch handles them directly. Each sample contains the input IDS, attention mask, and the label. Model configuration includes the Adam W optimizer, learning rate of 2 times 10 to the minus 5, linear decay schedule with warm-up, dropout of 0.3, gradient clipping. The goal is to fine-tune the entire transformer end-to-end. Both models were fine-tuned for 10 epochs. The training progress revealed interesting dynamics. BERT-based validation accuracy rose quickly and stabilized around 81% by epoch 4. Finber started similarly but showed more gradual improvements, ultimately reaching a slightly higher accuracy of around 82% by the final epoch. The loss curves for both BERT and Finber suggest overfitting happened. For evaluation, we employed a multifaceted strategy to capture different aspects of performance. The first one is overall performance metrics, including accuracy, F1 macro score treats all classes equally, and the F1 weighted score accounts for class imbalance. The second one is confusion metrics, used to visualize the distribution of prediction errors across the 3 sentiment classes. The third one is granular analysis. Classification reports show precision, recall, and F1 score for each sentiment class. And the fourth one is model discriminability, RC curves and AUC values to measure how well each model separates the 3 classes. And the last one is error inspection. It is a qualitative analysis of misclassified headlines to understand systematic failure modes. Now let's look at the test results, which clearly answer our research questions. Finber achieved the highest accuracy at 81.79%. BERT followed closely at 80.96%. The LSTM baseline trailed significantly at 73.04%. This represents a nearly 8 percentage point gain from the traditional model to the transformers, underscoring the transformative impact of pre-trained contextual embeddings. Furthermore, Finber's consistent lead over BERT confirms that domain-specific pre-training provides a measurable, practical advantage for this financial NLP task. The confusion matrices give us a clear visual understanding of where these errors came from. LSTM showed high confusion between adjacent sentiment classes, for example, negative and neutral. The neutral class was its biggest challenge. BERT demonstrated sharper classification. There was minimal confusion between the extreme classes, negative and positive. However, it still struggled significantly with the neutral class, with many misclassifications to both negative and positive. Finber achieved the highest precision for clear negative and positive signals. However, it showed a pronounced tendency to misclassify neutral samples as positive. A key insight is that neutral was the most challenging category for all models, while transformers excelled at separating clear sentiments. Drilling into per-class performance using classification reports reveals nuanced insights. LSTM showed moderate but balanced scores, struggling most with the neutral class. F1 score is 0.66. Bird-based improved substantially across all classes. It showed particular strength in detecting negative sentiment. F1 score is 0.80 and adopted a cautious stance on neutral with high precision but lower recall. Finberg excelled at the polarity extremes. It achieved the highest F1 score for negative headlines, 0.82, and the highest recall for positive ones, 0.91. However, it had low recall for the neutral class. The ROC and the AUC analysis reinforces this hierarchy of performance. All models found positive sentiment easiest to distinguish, and neutral the hardest. Positive had the highest AUC value, while neutral had the lowest AUC value. Transformers provide a major boost in discriminative power over LSTM across all three classes. Finberg secured the highest AUC across all classes, with its clearest marginal gain over BERT in the negative class, suggesting its training sharpens the detection of risk-related language. Looking at specific misclassified headlines reveals common challenges. The first one is misled by local phrases. All models can be confused by positive phrases within an overall negative context. For example, win streak. The next one is domain adaptation trade-off. Finberg's financial trading can lead it to overweight terms like challenging or interpret the end of a deal as strongly negative. Now to move beyond the test set and see how the model performs in a real-world scenario, we conducted a small case study. We applied our best-performing model, Finberg, to 10 news headlines specifically about Amazon. The results were very encouraging. For headlines with clear sentiment, the model produced high confidence predictions, typically above 97%. It also correctly identified factual neutral statements that lacked a positive or negative slant. For example, the headline "Amazon profits drop sharply amid big spending" was instantly and correctly classified as negative with 99.7% confidence. This practical test confirms that the fine-tuned Finberg model has strong potential for real-world deployment, capable of generating clear, actionable sentiment signals from live news feeds. As a final exploratory step, we compared Finberg's predictions for those 10 Amazon headlines with the stock's next-day returns. The initial direction results showed an interesting pattern. Negative predicted headlines had an average return of about plus 0.61%. Neutral predicted headlines averaged plus 2.23%. Positive predicted headlines averaged minus 1.80%. Crucially, this is not statistically significant. It's based on only 10 samples, and the store returns are driven by many factors. The primary value is in demonstrating a framework for future large-scale research into sentiment-return relationships. So, what are the main takeaways from this study? At first, transformers dramatically outperform traditional LSTMs for financial sentiment analysis, primarily due to their pre-trained, context-aware language understanding. Secondly, Domain adaptation provides a measurable edge. Finber's financial pre-training gave it a consistent performance advantage over general-purpose BERT, particularly in detecting negative sentiment. Lastly, the neutral category remains a key challenge even for advanced models, indicating an area for future improvements through better datasets or model architectures. For practitioners, Finber represents the most effective model for this task, balancing high accuracy with domain relevance. Future work could involve testing on larger multi-source datasets, exploring finer-grained sentiment scales, or integrating this textual signal with quantitative market data for enhanced predictive modeling. Okay, that concludes my presentation. Thank you for your listening.